CLion, a cross-platform IDE for C and C++. Download now.
So, yeah, about me, I'm a C++ specialist, and I'm not speaking anything today about C++. This is, the title is How to Write a Rubik's Cube Solver, but it may sound like I'm telling you how you should do it. That's not really how it's intended at all. It is more my journey about discovering how I could write a Rubik's Cube solver. This has been a hobby project of mine for the last half year, roughly. And it was, I never have done, well, at least not for a long time, any hobby projects. But I have a son, he's 13 years old now, and well, at the time 12. And I thought, it's time for him to learn to program a bit. So we have Saturday mornings, because he used to have Saturday morning school, didn't have any more after primary. And so we had decided we're going to do a bit of programming every Saturday morning together, a bit of pair programming. So let's use Python for that. Makes more sense. I'm not a Python developer, but Python is quite approachable. You can, with little experience, yeah, you can just learn while you're doing it. And so, yeah, I'm going to show you a bit, in a way, in the same way as I have been doing together with my son, and how we ended up writing a full cube solver. And we have many different ideas what we still want to do. And I'll show you as well how my initial approach was completely wrong. I knew it before I started, but that was the whole purpose. I was like, I don't know how to do this. And yeah, you can think and think and think, but maybe we should just do something very simplistic and then discover, why is this such a bad idea to do it this way? And then you can argue about it. Like, it is bad because of this reason. It's inefficient because of that reason. It's really fragile or hard to get right. And you introduce bugs that lead to, well, I have prepared a few slides so I can share that. It leads you to the common Rubik's Cube depictions. So when you, well, okay, so this is a project together with my son. So he is a speed solver. So he goes to competitions. And that's why we chose this as a project. Like, what can I do together with my son? Well, what has his interest? I don't want it to be like a sort of extra school session and I give you a task and that he feels, yeah, really unmotivated. And so we had this dream about doing something that would be exciting for him. And so Rubik's Cube related things was quite an obvious choice for us. So yeah, I'll show you. This is a recent competition, the last competition he did. And this should play a video. So I'm not very good at PowerPoint either, but there's a lot of delay, I think. I don't know why that is. Because I did it earlier and everything worked fine. That is strange. Have I deleted suddenly? No. That, yeah, okay. Okay, so you see the timer in seconds. So they solved the cube in 7.9 seconds. Yeah, so very quickly about how he started. 3 years ago, a classmate had a cube at school and knew how to solve it. My son knew that I could solve a Rubik's Cube, but we didn't have one at home. I never did it. And so he said, buy me a cube and teach me how to solve it. And so I taught him how to solve it in a very simple layer by layer way without hardly any algorithm. And yeah, that worked if you want to solve in 3 minutes. But of course, he immediately went to YouTube and said, what you have been teaching me, it's not the same, but it's a bit like what they call the beginner's method. He wasn't happy about that. He couldn't say like, look, I can solve it with the beginner's method or something like the beginner. So he immediately went to the advanced method. And advanced method, the most popular speed cubing method, is called CFOP. I don't know, by the way, here in the room, how many of you know how to solve a Rubik's Cube? Okay, that's a fair number. How many know how to solve it with CFOP? Okay, so that's one. So CFOP is the most popular speed cubing method. And with the layer by layer sort of beginner's method, you would need probably about 100 turns to solve the cube, and CFOP roughly in half the number of turns. So typically between 50 and 60 turns or something like that. Maybe some of you in the room or online expected me to speak about how to solve it, like with the God's number, the most efficient solution. Well, I have to disappoint you in that. That is a very interesting subject, and I may approach that in the coming year at some point. But it's a very different way of solving. But it is important for me to choose a representation that I could use also in that context for the cube. So you can have the most efficient, like fewest moves solved, that is. And so you can then always solve it in 20 turns or less, use a lot of computation power. You want it to be memory efficient because you have to search many different sequences and see what has certain properties and makes progress. But the speed solving method is for humans, and so and has to be recognizable in real time. There are human competitions for fewest moves as well. That is like you get 1 hour and you're allowed to come with 20 cubes and try different things with different cubes and make notations and try again. And you have 1 hour to find the most efficient solution. It's interesting, but it's not something I've done myself. Okay, so this CFOP, and I'll come back to the explanation a bit more. I wanted to show a little bit about when you see cube depictions. Well, if you know, I mean, the first picture here at the left, does everyone see that there's something wrong there? Yeah, so what is wrong? Yes, 2 greens on an edge and 2 blues on a corner. Let me see if I have like a cube here. So this is actually, this is not my project with my son. This is what I've done specifically for this presentation. I thought like, it's not really going to work for me showing here with a cube in my hand. So I need something bigger on a screen. And yeah, it's nice and big, that I can show, and I can have key bindings to do moves. But my muscle memory is pretty good with the cube. I can do things. So this is like 3 edges turned, and you see, normally I can do that much better, but now I'm doing a presentation, so I'm messing up. So my son, if he will see this, he will be so embarrassed. My son does these algorithms that take 20 turns in 1 second or something. And then I'm doing the fastest algorithm that you should do it half a second and I'm struggling. Okay, that's better. Anyway, so if you look here, standard, oh, that's not the one I had in mind. So if you look, you have here white on top, in this case, yellow on bottom. White and yellow are always opposites. Red and orange are always opposites. And blue and green are also always opposites. That is at least true for the color scheme that is used by everyone today. It wasn't always like that in 1980. If you bought a cube, you may have a different color scheme. But you would never have something like this. And here, what do people see with the second cube? What is wrong there? Exactly. So that is another thing that not everyone always thinks about if you don't know how to solve yourself, that the centers are always fixed relative to each other. So it is a fixed core, they don't move. If you only use the outer turns, the centers stay put. And yes, you can rotate the cube, but that is really looking from a different angle at the same cube. So centers don't change positions. And these artists, they just think somehow that the stickers individually move around. And yeah, this is one of my annoyances with T-shirts with cubes, with all depictions, that you hardly ever find a cube that is actually solvable. And yeah, so here it's not as obvious, but on the current color scheme, like a corner with white and yellow, that that is not possible. But well, and here again, maybe someone else can see what is wrong here. Yeah, 2 white centers. This is reasonable, but again, there's a corner with a white and yellow. I think here is the same. There may be, and sometimes there's other problems like this is very old one, so we don't look at the white and yellow on the corner, but it has 2 blue-yellow edges. So this is from the 70s, before any of us had ever heard about the Rubik's Cube. The cube was invented 51 years ago now, 1974, by a Hungarian Ernest Rubik. And for the first, I don't know, about 5 years or so, it was really only in Hungary. And then suddenly, like 1979 or 1980, it went global and there were toys companies selling millions of cubes around the world. Yes, so let's get into a bit. Let's see where we were, because I made a mess of things, so I apologize already for that. But you know what? Because I was messing about. Let's completely clear here. Yeah, by the way, I don't know, does everyone have experience with notebooks or how? So here, instead of the imports, I've now done this instead, because there were a few things that didn't work how it should work in the notebook if you just do normal imports. And one of the most important thing was was using some code inspection. So you say inspect get source, and then it should show you the function definition. And then it showed like the wrong function. And yes, asking ChatGPT like, what is going on? Why is that? It told me, yes, if you're working in a notebook, that can happen. You may want to use %run to get it in the local context. and then that should work. Yeah, so here's some other helpers. And yes, so I wanted to look a bit more at the properties of the cube here. So let's see if I can undo this. Yeah, one of the questions is we saw some obviously wrong cubes with two white centers and so on. But say I take this cube apart physically and I put it back together randomly, then people that have had a cube and that may have done that discovered that you most of the time you can't actually solve the cube anymore. And so one of the questions is, yeah, what is the probability actually that it's solvable? And I don't know if people have any gut feel for that. Is it 50%? Is it a quarter? Is it less? Or what cannot be solved? And so there are a number of independent issues. And I will come back later as to why that is. But if you have one flipped edge, for instance, that you can manipulate the cube however you like, you can never solve that. It turns out they call it OLL parity. It's you can flip two pieces, two edge pieces, no matter where on the cube, always a pair, so always a multiple of two, never one. So that is one issue. The other is a corner twist. And you can actually accidentally have that during a solve that a corner turns. With a modern cube, with a modern speed cube, they are much looser, which is very good for fast turning, but you may get accidental corner twists. So in a competition, you are allowed to physically twist the corner back in the correct position if it got twisted. Obviously, you're not allowed, if you have this situation, to say, okay, I'm going to twist this one and I'm going to twist that one to solve it. But if one got twisted, if you stop the timer, it's a failed solve. It's a DNF, did not finish. You have to physically twist it in the correct position and then stop the timer. And believe it or not, I saw recently an 11-year-old who happens to be the fastest cuber in the world, but he had that problem, corrected the twist, stopped the timer, and was 5 seconds. So these fastest cubers, it is unbelievable. They turn with a turn rate at the maximum up to like 25 turns per second. And on average, from the beginning to the end of the solve, including pauses, this boy, Yi Heng Wang, he's called, he managed to get like 14 turns per second on average, including his pauses, recognizing. And it's just mind-boggling. Okay, but to come back here, so when you twist a corner, that is not solvable. Let's the one key. Yeah, so this is also not solvable. So you have three positions for the three orientations for a corner. And if you do a turn, for instance, this, you can see that the I'll come back to that when I'm numbering the pieces, but it's always a multiple of 3. So you can never have an orientation that has a remainder when you look at all the orientations of all the corner pieces. So that is one of the things. And then there's this. You can have a pair of edges swapped, but no other pair swapped. This is also not solvable if the backside is solved. So you can solve this two pieces, two edge pieces, but then also either two other edges swap or two other corners swap, or the centers are unsolved. And so that is something I wanted to show actually. So I can just close this, and this one. So if I have that situation, there are cubes called void cubes that don't have centers. So you can actually look through them, but you could simulate the exact same effect by removing the center caps so that you don't know which center is which center. And let's see. So if I imitate that, this can be solved if you have a void cube. That also means you may encounter this situation on a void cube. And if you know how to solve a regular cube, you think like, well, just removing the centers, why would I not be able to solve a cube that should be easier to solve? But yeah, you may encounter this situation. And so this is one of the ways to solve this situation on a void cube. And so now when you look at the back, it really is solved. But when I put my center colors back, then you see, so that is what happened. On a void cube, you may have, in a way, the centers that you can't see, they may be in the wrong place. And so we have these three different sort of causes why a randomly put together cube may not be solvable. So we had the edge flip, we had the corner twist, and we have a single swap of two pieces. And so that means that 1 in 12 randomly assembled cubes is actually solvable, because you have a half and a third and a half again chance that you have the correct configuration. So I thought that was interesting. And then you think about how many configurations are there actually? And everyone knows that it's pretty big number, but let's have a go at if we can see if we can actually calculate. No, I'm going to first. Actually, let's go back. Can I undo this? Not that one. That one, yes. So yeah, I'm thinking now a bit about the best order in the presentation, but I may come back to this later. So if I will come back to it later, let me put it that way. If I now go back to the project with my son, and we wanted to start implement something, and we had no idea how to go about it, and say, you know what, let's just say we represent yellow with a Y and W for white, and it's luckily the colors all have different starting letters. So you know what, I define my current scrambled cube in a string, and then I initialize my cube object with that, and it can put it in some, well, I would call them arrays, but in Python they're called lists. So multi-dimensional array I have in mind, and yeah, that should be my proof of concept starter approach. And so I did that. I'm not going to show you the code directly, but if I print this one, I get the thing back, but the actual representation is really like, you have a use side, for instance, and it has just this list of lists for, yeah, when I say U side, U is the top layer, is called U. So there's a standard notation for the right-hand side is R, left-hand side is L, the front is F, the back is B, and because the back is B, yeah, you can't also say the bottom is B. That doesn't work. So the top and the bottom layer are like up and down. So they're called U and D. And so that is the standard notation. I may even have a slide for that. I'll come back to the scramble. But here's the turns. And in addition to the outer turns, which is all you need to solve, really, there are also notations for wide turns, because as a speed cuber, it might be better to use wide turns to achieve certain things quickly. But a wide turn is exactly the same as a single turn plus a rotation. So it's equivalent, but it feels very different. Then you have the cube rotations, X, Y, and Z. That's just the whole cube rotating. And then you have slice turns, which again is equivalent with 2 outer turns and a rotation. But yeah, when you do an algorithm, this doesn't feel like you're rotating the cube. You're doing like, you're doing slice turns. And because we wanted to implement CFOB, the speed cubing method, we need to support those turns as well. Yes, so to come back here, it was very quickly that when I started to implement individual turns, that it was awkward. You're basically getting the problem of these cube depictions. You're manipulating individual stickers. So it is too much work. It's error prone. It's the only thing it's good for is when you want to print it out again, it's convenient. But even that, if you just print it like this, that is not really for a cuber. These letters, that it's not recognizable, right? You recognize patterns in a way like as here, like in this. You recognize patterns by the color patterns. And so to unfold a cube is already a bit awkward because you don't see so much which colors come together at the back in what way. But this is a standard depiction that is used, especially for scrambles. So this is how it works in competitions, and also every competitive cuber, when they practice, they use some app on their phone, produces random scrambles. So you start with a solved cube, you do the sequence of turns that has been generated by the app to give you a completely randomized state of your whole cube, but it's repeatable. So you can do it and you say, look, I have a new personal best, and I did it on this scramble, and you can try the same scramble, or you can reconstruct exactly how you solved it. And someone else can analyze that specific scramble and say, well, actually you missed some opportunity because there would have been a better way to solve this, and things like that. So this is a good way to ensure that you've executed the scramble correctly, because you do this sequence and then you check, that side is the same. Yes, I've done it correctly. But otherwise, it's easy to make a mistake. So the very first thing we did was like, okay, I'm in a notebook. I'm pretty sure the notebook can do colors. I didn't know how or what. So again, we did a little bit of pair programming with ChatGPT. And it says, well, yeah, install pandas and do some frame and use the display magic of a notebook. And so I did some ugly hacking. And then, hey, now I have the same as I had here with the letters. But now suddenly it starts to look like a cube. This means something to cubers. When they see this, it starts working in their brain and they recognize things. I have to say, it's still nothing compared to actually having a cube like this. And now, because I did that three-dimensional cube, first time in my life I used the games engine. So yeah, that was also a little bit of fun. I can show the same scramble. I don't even know which scramble this is, but oh, something went wrong there. Oh, that's new. You see, I managed to break this since last night, since this morning. I don't know. That is not what I expected. Okay, I know why. It is because I have a... Okay, I'll don't do it on this. So this is the old representation that we implemented to throw away, and yeah, so I don't actually support that one with this new three-dimensional cube. But what very quickly became clear to me is like, okay, we have a cube object, and we can rewrite that cube object a number of times if we need to with the representation, but we need to be able to use this standard notation for the moves. So we can say, I initialize a cube with this scramble. So I give it the standard notation for the scramble. And then I can say, do this sequence of moves now, do this sequence of moves. And I added the facility that you can put comments for every sequence of move that you do. So that is the cube object. But then the sequence of moves, you want to be able to manipulate them as well. So you have now, you want to enter them in a string format, but you may want to reverse them. You may want to mirror them. You may even want to rotate the turns. So that is a little sort of sequence turn manipulation library that you want. And so we started with that a little bit because that seems sort of quite suitable for my son to start with. So, okay, I have this sequence of turns, I have another sequence of turns, and I want to concatenate them. As I already said, I didn't think string representation is the representation you want for all these manipulations. So it seems much more logical to store them internally as a list of turns. And a turn, also you don't really want to represent as a string. That is sort of an object in itself, which you have the type of turn. Is it an F turn? Is it an R turn? But you also have the count. Is it one clockwise, one anti-clockwise, or is it a double one? And interestingly enough, it's important to also be able to say, it's not one counterclockwise, it's 3 clockwise. So it's equivalent, but for SpeedCuber, it may not be in terms of execution speed, because regrips are expensive. And you may have your hand in a position that, for instance, this is an algorithm that often R3 is used. So move your hand, and now 1, 2, 3, and then you continue. So, and then I don't need a regrip. I can continue. But if I had done one more R turn instead of the R3, yeah, then you needed the regrip and you would lose time. And there's others as well here at 1, 2, 3, and it is not completely uncommon. So yes, it's maybe only 1 in 100 sort of algorithms. And when I say algorithms, I just mean a sequence of turns. That's speed queuing terminology. So not as a software terminology. And yeah, the speed cubers, they literally learn hundreds of different algorithms that consist of anywhere between, yeah, say 8 and 20 turns or so. Yeah, so we implemented some of these simple, let's just add it here. If I have that, let's just play around a bit, because my notebook's got a mess of different notebooks. And so if, for instance, I wanted to, I say this is a sequence, and then I have say another sequence, and it could be doesn't matter, it's a short sequence. And then you say, I want to concatenate them, for instance. Then this is the result. So you see, the sequence is basically a list of turns, but it's its own object that derives from list, so that we have this conversion to string, which is convenient. But other than that, you can just use it as a list. And yeah, you want to maybe, when I say you may want to inverse. And so with this is, if you see inverse, what is the inverse of a sequence in cubing? Well, that is the sequence that undoes the original sequence. So it's not just going from right to left, but every turn that you do needs to be inverted, which means if you do an R clockwise, when you invert it, it should be anti-clockwise. And so, yeah, these were some simple things that we could get started with my son. And let me see how simple something like inverse is when you do it in Python. This is the whole function definition, because Python has a built-in reversed. So I say I put it in explicitly in a sequence object so that you can support calling it with string, and you reverse it. You just say, I will start with an empty one and I just append it. And the turns, I have a turn object. Turn index that's how I represent turns. They just have a numerical index for whether it's an R or an L or a U, and I have a count. And the count, initially I did modulo 4. Well, actually, I didn't do straight modulo 4. I added one modulo 4 and then I subtracted one, because normally you have either you have what they call an R prime, R, or R2. And so the apostrophes in the notation, they are pronounced prime, and they are the anti-clockwise turns. But as I said, I wanted to support something like R3. So I can have another function to canonicalize it, for instance, and I had initially thought, okay, if I have implemented canonicalized function, then I can compare two sequences. Are they the same? Yeah, that turned out to be a bit more difficult problem. Because yes, it is easy to see if with the simple canonicalized form, are they two same lists? But it turns out there are many equivalent lists that look completely different in turn sequences. And there is no simple way that you can write it in a canonical form to then do a comparison. So the best way is to say, I have a cube object, I apply my sequence to the cube, and do I end up in the same state? Yeah, and that works very well. So we saw that, or I shared that the initial representation was really no good for me. And I had implemented this sticker swapping. I had implemented it and then say, it is an R2, so do the same thing twice. And so it became inefficient, fragile, and I needed a better way to represent it. And so then I thought, you know what? It's clear when you understand how a cube physically works that a corner is a corner that can never be swapped with an edge. Corners have 3 stickers or tiles, edges 2. And so I can just number my pieces, and every piece has a position on the cube and an orientation. And I had the idea that instead of storing the tuple of position and orientation as state, I can combine them in a single state number. And so if I go back to this cube, I said, okay, let's start with the corners. And actually, this is something that my son had a big influence in. He told me what sort of considerations we needed to take into account for it to be useful, to have useful properties that you, and I mentioned already this position and orientation. So you want to be able to, as easily as possible, derive what is the position and orientation. You want to separate the two concepts, basically, and still have a single state number representing both. So I say, well, you know what, for corners, I say, if a white sticker faces upwards or downwards, that is the base. That is my oriented corner as orientation 0. And the same for yellow. So I number 4 corners, 0, 1, 2, 3. And then if you look in the bottom, same For yellow, 4, 5, 6, 7. There are only 8 corner pieces, so that is my corner pieces numbered. But we also need to represent the orientation because, well, you can move. Oh, this happened a bit too quickly, so it went to the. What I wanted to do was here. My piece number 2 is in the same position as it was originally, but now it has a different orientation. And this is 1 turn clockwise. So if you look at the original number, was 10 was in that position because it was red, right? So I have 8 pieces. You know what? So 0 to 8 means it is in position 0 to 8 with orientation 0. Now, if I continue to count, number 10 here means it is 2 modulo 8. So it is, it has still position 2 as it had before, because it was 0, 1, 2. Still position 2 because it's modulo 8, it's still 2. And if you divide it by 8, then that is 1 rounded. So you decompose the numbers in how many times does it divide by 8 and what is your remainder. And the remainder is your position. And how many times it goes into 8 is your orientation. And the orientation of corner pieces is 0, means white faces up or down. And a twist clockwise is orientation 1. Another twist clockwise is orientation 2. So you see the green 18, that is again another 8. And yeah, I think that turned out to be a very good decision and representation. And so we took the same approach also, of course, for the edges. There's 8 corners. Every corner has 3 possible orientations. And there are 12 edge pieces, and they have 2 possible orientations. So both piece types have 24 possible states. And this is not something I've implemented. I've done the centers, also simple counting them 0 to 5. But a better way of doing the centers is say, it's actually one piece, it's the core. And so we have one core piece with 24 orientations. And so why is it 24 orientations? Because you have 6 sides. Every side could be facing up. And when a side is facing up, you could have 4 ways that it's facing up. You can turn it around. So I think that's actually, yeah, purely coincidental, but it's interesting that the 3 different piece types all have 24 states, even though they're very, very different. So yeah, I can, you see, I'm not good with these key bindings. I want to undo something and then, so let's see, I can switch those off. So a similar idea with the edges. I say, I start counting them from the top, 0, 1, 2, 3. Now it's slightly more tricky. What do you consider oriented and what do you consider unoriented? And my son was very clear about that. It was immediately obvious for him. He says, can't you tell? 4 and 5 are oriented. and so are 6 and 7. and obviously 17 and 18 are unoriented. That is a whole theory for speed cubers. They speak about good edges and bad edges. So this is how you have to think about it, is that when you're solving an edge piece, if it is a good edge, you can solve it with R moves and U moves and D moves and L moves, but you never have to rotate the cube and you never have to use F moves or B moves. And F moves and B moves are less popular with speed cubers because it is slower. So it depends a little bit on the combination of moves. You may be able to do an R prime and F together very quickly. But in general, F moves are, and especially B moves, are a bit awkward. And rotations are also slow because that's the whole regrip thing. So if an edge is oriented, it's very good. It means it's a nice spammy solution, as they call it. So then you can get this high turn rate. Yeah, so that's credit to my son for numbering the edge pieces. He said, okay, 0, 1, 2, 3 is like this. Then we do 4, 5, 6, 7 like that. And then we do 8, 9, 10, 11 like that. And so they are our oriented positions. And because there are 12 pieces, if you add 12, you get the unoriented orientation of the same position. Yes, so that is our numbering scheme. And so then we said, okay, so now our state consists of the tracking the individual pieces. So I have a list of my edge pieces, what state they are in. So that means what position and orientation are they currently in. And I have the same for my corners. Corners and edges don't interact with each other, so you can completely process them independently. And I also do my centers, but as I already said, it's better to work with one core and what orientation does it have, but I've not got around to implementing that. But because I've completely separated code for solvers, code for sequence manipulation, and code for your cube state, it's very easy to re-implement some cube and OI solving code will work with it. And all these solvers, even if the solver depend on a specific numbering scheme, they are not interested really in centers. So let's come back to what I said before. How many configurations do you think that there are? We know it's a big number, but yeah, let's have a go now. We probably have a little bit better understanding as a result of our. Well, maybe I keep here. So can I switch this? Yes, that looks better. We understand a bit better now with the positions that they can all be in and the different orientations. So let's have a go. Let's see. Yeah, by the way, I don't think I showed this, but we actually did the numbering this way. So we didn't have this three-dimensional cube, and so this worked, reasonably well for us, and could use it as a sort of reference when we were programming. Where is this number? And let's see. I had prepared something somewhere. Yeah, memory use. Let's see, where did I? what I was talking about, that things became a mess. Because that's memory usage. And so I may have to go to another. This one somehow got lost. No, that's, right. So the header there, this is not memory usage, so that's why I confused myself. By the way, is the font size good for everyone, or is it a bit small? I might be able to, so it's a bit bigger, that may help. Yeah, so the we have 8 corners, so we have all the possible permutations is 8 factorial. You can have any combination of positions for corner pieces. Then we had 3 orientations for in every position. So you see here 3 to the power 7. Why would I write 7 here and not 8? Anyone an idea? Yeah, because you have your last corner can only be in one specific orientation. And I was going to show that with the numbering scheme, that you can actually see that if you do a single turn, that no matter what you do, the sum of the orientations will always be a multiple of 3 for corners. The sum of the orientations for the edges will always be a multiple of 2. Okay, so we have here 8 factorial. We have 3 to the power 7 for the orientations. So you multiply them to get all the corner configurations. Now the edges, you have 12 edges. So if factorial of 12 for the permutations, you have 2 to the power 11, again, because you have the parity, for the orientations. And if we actually evaluate this, then we get a pretty large number. So this is called 43 quintillion. So that's 43 with like 18 zeros. And then, yeah, that is so large, it is hard to comprehend. How do you compare that with something else? So I thought, like, well, what is some other big number that maybe we can give some sort of meaningful comparison with? So it's like, well, you know what? The Big Bang, that was quite some time ago, apparently about 13.8 billion years. So, okay, how many seconds is that roughly? 13.8 billion years. Well, there's 365 and a quarter. So days in a year. There's 24 hours in a day. There's 3,600 seconds in an hour. Okay, so that's number of seconds since the Big Bang. That is pretty much exactly 100 times less than the number of configurations on my on my cube. So if you start enumerating all the configurations from the Big Bang onwards, 100 times per second, then now you have had them all, if you haven't had any duplicate configurations in between. So it's mind-boggling, really, how large these numbers get. And then there's still people that look at the cube and then blindfold themselves and just solve them. Which is interesting. I've looked at how the mechanism for that work as well. I do see that we are actually going very quickly with time. I thought an hour and a half, that is so long, how can I fill an hour and a half? And now I have hardly started. Yeah, so let's get into some of the things that I really thought was interesting to share relating to solving. So the first thing with solving is with CFOP, what do you solve first? It's the 4 cross pieces in the bottom. So let me quickly run through an example solve. So that is a bit messy. For instance, here, this is not code I wrote. This is actually a website, alk.cubing.net, that is very, very good for sharing your solution with someone else. And I've embedded that in a notebook here as well. So this is my scramble, my setup. So when I click here, this is a scrambled cube. I always solve with white center on the bottom. That is what I teach most people to start with. Real pro cubers, they're color neutral, as they call it, and they look at this scramble is best solved with the red center on the bottom, for instance. So that's another thing. I wanted to be able to have my solver work in any orientation of the cube. And that fixed numbering system that I showed needs to support re-indexing then, that you say, okay, I rotate, I want to solve in this orientation, please renumber my pieces. But if I quickly showed like how you start is want to solve the 4 pieces in the bottom here around the white center in the right position, so they do connect with the colored centers. And there are no standard algorithms or anything for it. It's just an intuitive puzzle, and experienced cubers, they look at this scrambled cube for like 5 seconds, and they can close their eyes and do the 8 turns that are required to solve it. Probably you can train some AI to do it as well. That's not how I have approached it, but I've approached it with pretty brute force solving. But we can have a quick look at if you just manually solve it, that you say, okay, I see here 2 white edge pieces. That one is connected with the center, so it's easy. You can put it down, it's solved. That one there is also connected to the center. So this is actually an easy scramble. But I have 2 pieces here, the red white and the green white, and they are in the wrong order in a way. If I put the green down first and then the red down, they're swapped. So that is like a little bit awkward. You could put that one down first, but then you need to put it at the correct side of the other one. So this is now a little bit big, but I can. So you do 2 in the D layer before you put that edge down. So now they're correct relative to each other. And then you can put them at this stage in the correct position, because we know that the other 2 cross pieces can then be put down, and that solves the cross. But sometimes you solve all the cross pieces correct relative to each other and then adjust them to be in the right position to connect with the centers. So we'll go very quickly through the crosses solved, and in CFOP you solve corner edge pairs. So you don't solve first layer first and then the second layer. You say, I have this corner piece, that edge piece, this is in this position, this orientation, that is that position, that orientation. You could basically list all the different positions and orientations and what are the most efficient way of solving it. But it gets quite long, the list, because if some other edges or corners haven't been solved yet, you can exploit that and do it more efficiently. And I can show you, like, on oh wait, I had here something. Here, this is a document from a famous JPerm YouTuber, and he says like, in this position, you do these algorithms, that you do that, if you do that, you do that, you do that. And so there's actually quite a bit you have to learn if you want to solve it so efficiently and fast. There's more, and then there's more, and yes. And yeah, it's pretty crazy how much you may have to sort of recall instantly, do the right thing. I have not implemented all this. I have, for the first two layers, implemented basically layer by layer for the moment. It's not interesting for you as sort of non-cubers to go through this anyway. So I wanted to focus on that, and I don't have much time. I did not realize it would go by so quickly. So let me see, do I have to? I need to skip this example. Solve, and I don't even have the cross solver here. Let me yes, okay, I'll take that one in this notebook. So now this is how display cross solutions. What happened here? This is not cross solution. Okay, this move solution. No terms correction. Okay. So the cube that I start with is a solved cube. Yeah, so that doesn't result in. Yeah, so let's, because I had shown you the example of how to solve it, then by that time that cube was solved. So yeah, that confused me. So the cube that specifies what is the scramble, and also what are the moves done after that scramble, but it looks at the current state when I present the cube to a solver. Because, well, for a cross solver, you could argue maybe I should just look at scramble, but you operate on the state, so you need the current state. It doesn't. So where was I? Here. So if I just put this here, that's better. So this is what it came back with, and it found a few other 6-move cross solutions as well. So it always finds an 8-move cross, but I have here a little bit information, and I should be able to do a print def of this, so we can actually see what it's doing. And it may have printed it somewhere. Yay! So this is my full code for doing the cross in a brute force way, that's not it. That one I need. Yeah, I'm like, this is just printing. This is not. So it's, and that's probably it. Is that? Yeah, that's what so that was what I feared for, solver. Bum, bum, bum. Okay. Yeah, so we have this list of 3 piece types, centers, edges, and corners. And so I basically query my cube. I say, well, select the part of the state I'm interested in, which is the edge piece type pieces. So this is actually just a constant with a value 1, because it's just 0, 1, or 2, but I like to give it names. And I say I'm interested in the edge pieces number 8, 9, 10, 11, because that's how we had numbered them. It was 0, 1, 2, 3 on the top, 4, 5, 6, 7 in the middle layer, and then we had 8, 9, 10, 11 in the bottom, and we want to solve those 4 pieces. But the state will give you the positions where they currently are. So I said, well, you know what? I want to have some sort of cost function that says, how close am I to the solution? I don't know exactly how close I am, but can I have a very simplified estimate how close I roughly am, that I know if I'm a random turn, or in the brute force case, try them all at a certain stage. How can I tell whether this may be going in the right direction or in the wrong direction? And it's okay to go a little bit on your measure in the wrong direction before you go in the right direction. You can just keep a lot of states in memory. So I said, you know what? In C++, I may use some multi-map, which is my estimates, how many turns away am I if I estimate it based on individual pieces. So I say, well, this edge piece is 2 turns away from being solved. This edge piece is 1 turn away from being solved. This edge piece is 3 turns away from being solved. You know what? Let's try something very simple. Just add those 4 scores up. Clearly, lower is better if they are only like 1 or 2 turns away from being solved in total, then I'm almost there. And if they are high, lots of 2s and 3s, then I'm not very close to a solution. So I said, well, let's use something like a multi-map, which has the score as key. And so it's ordered. And I may have a cluster of partial solutions after I've tried 1 turn or I tried 2 turns. That say, well, okay, these partial solutions all believe they are 5 turns away or so from being solved in total. And then I go to the next stage, and then I keep a decent number around. And the ones that have really much worse scores, I can forget about those for the next round. So I thought like, this is going to still be too power intensive, because it does explode quite quickly, the number, if you would keep them all, because you have 6 possible turns. And yeah, if you may have to do 8 turns to solve the cross, then you have like 6 to the power 8. It's a big number again. But yeah, if I say I keep obviously the best score I have so far in this round, but also the ones that have a score that is 1 higher or 2 higher. But if it's 3 higher than the best one currently, I say, oh, forget about it. And that seemed to work very well. I have tried it on specific scrambles that are known to have the worst case 8-turn solution as best solutions. And still in Python, that is very inefficient. I didn't get around to showing you how inefficient even storing this state in this way is, because I'm a C++ developer. I expect, like, in C++, the integer is like 4 bytes or so. It could be 8 bytes. So I thought, like, well, in Python, I know they support big numbers, probably have some extra data structure that uses another 4 bytes or maybe 8. But I didn't quite expect it. My number from between 0 and 24, like 28 byte each. And that is just for the number itself. Then the list structure has overhead, fixed overhead. And then on top of that, it has a pointer to your numbers for every entry in the list, which is 8 bytes again for every number. So that does add up very quickly. But yeah, so this is one example here for 6 move cross. I didn't get to show either, but my son implemented very early on a generate scramble function. And we can do that here. So every time we get a different scramble, I don't. Oh, it found only one other. So it's this quite interesting. Now I had one with sort of 4 solutions of 6 move cross. Now another one with a 6 move cross and only one other. And sometimes you get like 97 different solutions for your cross with all the same number of moves. So I did have here some, basically for debugging purposes, but you get a better idea of what it's actually doing. So after 1 turn, it says, I found best a sequence with a score of 6. Then I also found 6 other sequences with a score of 7 and 6 sequence score of 8. And then some with score of 9. And then for the next round, I continue with, I think, the 3 best ones. And so this is the progression of this brute force but prune approach. I see that I have very little time left. I'm not able to explain some of the interesting things I wanted to explain, but let's jump to PLL. So to quickly show, OLL is considered the orientation of the last layer. So after you've done the first 2 layers, you do in one algorithm, you fix the orientation of all the last layer pieces. And there are 57 different algorithms to cover all the cases. But with our representation, and if you calculate, how many different cases do I get when I calculate, like, this piece could be in 3 orientations, that piece could be in 3 orientations. And then I come to 216. And I was like, how do we map my 216 to my 57 algorithms? And so then I understand, well, yeah, it doesn't divide. So I was like, clearly, you can have the same pattern and rotate it. And so that is the same algorithm you apply. But it's not 4 times 50, 57 or 50. And then I was like, hey, 57 or 58, because you also have the skip case where you don't need to do anything, where everything happens to be solved. So it's symmetry. So if you have the skip case, it's the same in all directions. There are other patterns that are clearly different in 4 directions. So you have to do the correct setup turn. And so the 216 contains this skip case exactly once in the table. But the ones that do not have symmetries, they show up 4 times. And so there are some that show up 2 times, some show up 4 times, and then it all works out. And so what I did was I went backwards and say, start with a solved state cube, do the inverse of all these algorithms. Then I calculate what my orientations are. Then I say, okay, edge pieces have 2 orientations. So it's like a binary number. The 4 edge pieces represent which orientation the edges have. The corners is like a ternary number, represents the corner orientations. I combine the 2 in a mixed base number. Why not? So I have one number that can index my 216 table. And I just need to append the specific, well, you move the setup to get it in the right orientation to apply the algorithm. And so, yeah, that worked really well. So I didn't need to manually do anything, basically copy paste of a list of these sequences. You invert them, execute them on the cube. You calculate what is my orientation code with this binary ternary combination. And then you have with the setup turn your solution for recognizing, calculating the code, go straight in an index rather than having to do some dictionary lookup. So I did the same idea for the PLL, the permutation of the last layer. So there are 21 algorithms, so 22 cases because you have the skip case. And unfortunately, I don't have much time for that, but I came up with a way to, so you have all the permutations here listed, a way to calculate an index for every permutation. So it's easier with the orientations because you can directly represent, this one has this orientation, that one, and they're like digits. Well, with permutation, once one is in, it's like a factorial, and once one is in a position, another one digit can't be in the same place, and it would be inefficient to encode them independently, separately. So what I did was I come up with a numbering system with sort of factorial basis, and I say, okay, the first one I encode directly, so that is basically you're weighting 3 factorial. But then the ones after, I look like, hey, do they have numbers greater than the one I've just done? We know that's not going to be 0 anymore. That's not possible anymore. So I subtract 1 from all the ones that are higher than the ones that I've already processed. And then you end up with this number system that has weightings based on factorials rather than powers over base. And that nicely makes your mapping from having observed the permutation based on your state. That gives you direct permutation. And you can calculate a number which then can index exactly which PLL algorithm you need to apply. And there, again, you have this symmetry. So the 22 cases, they they map then to 244 in your table. And the table that's interesting. So 22 algorithms, small number, but the 200 the table for the PLL is larger because you have a potential setup turn that you need to do before you execute the algorithm, and then there's a final adjustment to solve the cube. So you have potentially 4 different ones before you do the algorithm and 4 different ones after you've done your algorithm to finish solving the cube. And yeah, so that all together gives me a solution I can maybe run a full solve. Let me, do I have a CFOP solve? I had it somewhere in the notebook. Here, maybe. This. So this is, and okay, so I found this as a cross, as a, this is actually, yes, more like a beginner's approach to the first 2 layers. And I specifically implemented many things with a lot of comments because I wanted to share like a link. I can make it a tiny URL from this, WhatsApp it to someone, and he opens it in the browser and gets to see this, how to solve it. So for people that are still learning to solve it all, I can provide the link, and it explains the different turns it's doing. So it actually says like, I'm now solving this corner, or I'm now solving this edge, and I have different configuration to do with different level of verbosity, and or whether I combine different things into one longer sequence and just say I'm now doing this part of the solve and little comments, or I'm explaining like I'm rotating now because of this, and now I'm doing one U-turn to set it up and that. And so this is a little bit compromised, but I had the even more verbose version where the setup turns, the U setup turns in the beginning you see here, are separately explained. Oh, now that's in the second layer here. So this is the most verbose mode. But the last layer I do with CFOP efficient solve here. But I've also been implementing that in multiple steps, so I can use it as a teaching tool. It's not, so we had many different use cases that went a bit quick that last bit, but when I go, let's shoot, okay, yeah, so this is not what I expected actually. So this is not with the full OLL. So maybe the default configuration was not to do the full OLL how I had explained. But I have different configurations. So you can say, I want to use this method for OLL. I want to use this method for PLL. I want to do this method for the F2L, first 2 layers. Yes, if anyone is more interested in what I've been working on, feel free to contact me. And yeah, does anyone have any questions?